Welcome to Module 21, Completion of a metric space. We have defined the concept of what is a complete metric space. So we want to now define what is the meaning of completion of a given metric space. So we shall describe this construction, a process which assigns to each metric space XD another metric space XAD DAD, that is the notation we have set up, such that the first condition is this XAD DAD is a complete metric space. It has to do something with the given metric space after all. So all those conditions are explaining that in the 1, 2, 3, rest of them. So there is an injective mapping eta from XD to XAD DAD, which is distance preserving. In fact, any distance preserving map is automatically injective, that we know. Okay. So injectivity is emphasized here, but it's a consequence of distance preservingness. The image eta x is dense in XAD. Any isometry f from x1 d1 to x2 d2 extends to a unique isometry f hat from x1 hat d1 hat to x2 hat d2 hat. This is what I meant by, instead of just describing XAD DAD, it's a process. Okay. So I can't explain it more than that, but I will use just to throw a word. This is like what one calls a canonical or categorical. It's like a functor and so on. Okay, so that is the third part here. Any isometry f from x1 to x2 extends uniquely from x1 hat to x2 hat. The fourth one is, if XD is already complete, then eta itself is an isometry. In other words, up to isometry, we are not doing any new thing here at all. It is the old XD itself. Something is already complete, then there is no completion. Completion itself, XD itself is its completion. So in what sense? Isometrically. So because the construction has to be there for more general space, things, then you have to, in the special case, it will not be just XD, but some copy of XD. Copy means what again? Isometrically. So this eta itself is there, the canonical embedding of that. That will be surjective, that's all. Okay, it's injective. It is isometry, it is surjective, the inverse will be also isometric. So these 1, 2, 3, 4 explain, okay, the relation between XAD DAD and XD, the one which we have started with. Okay, so let us start with the construction. So this XAD DAD will be called completion of XD, that's what. One point I want to remind you, if you have done the metric completion of R in your analysis, then the process that I am going to do is half of that work, only 50% of that work. The metric completion of R starting with Q is exactly like this in the first half, and then there is more work to do there. Here we have less work to do. On the other hand, if you haven't done it, at least half of that part you will be learning today. I will not do the latter half, but I will later on, if time permits, I will just explain how that is also done in the case of real numbers. So what I mean to say is here, you start with the rational numbers with the standard metric, namely distance metric, that we know that's not complete, right? When you complete it in this process, what you get is real numbers. So this part we will not prove now. Okay. We will only show the process of constructing the real numbers is similar to this one. That is what I want to emphasize. That's all. So the motivating fact is the following. Suppose we have two sequences A and Bn in X such that both of them converge to the same point X. Then of course, the first thing is both are Cauchy sequences. Moreover, both the sequences are coming nearer to that point after a certain stage. That is the meaning of that, right? So in particular, they will be nearer to each other. So how do we express that? There exists epsilon, for each epsilon there exists n such that after that, so m is bigger than or equal to n, the distance between am and bm, the same m, okay, this will be less than epsilon. Okay, this all that you have to do is you have to use triangle inequality here. So I will leave it to you to verify this one. Okay, two Cauchy sequences converging, then they will be nearer to each other by this definition. Okay, so that is the starting point, which just means that you could take, instead of X, you could take a neatly chosen Cauchy sequence. Since there is no way to choose a particular Cauchy sequence, what we would like to do is take all sequences, Cauchy sequences converging to that point to represent that point. Now, when that point is missing, see, if that point is there for every Cauchy sequence, then it's complete already. When that point is missing, the Cauchy sequence will be there still. Look at all the Cauchy sequences. How to pick all of them? They must be nearer to each other. So that is why we come to this one. Take X twiddle, denote the set of all Cauchy sequences Am in X. Now I define a function x hat x twiddle cross x twiddle to 0 infinity by the formula d twiddle of AB. This A and B are now Cauchy sequences. Okay. Take the limit of d of A and Bn as n tends to infinity. So this is motivated by that. If An and Bn were converging to same point, then this distance would have, limit of this distance would have been 0. So that is our motive. In general, what we do, we take this distance to measure the distance between them. So this is the measure. That's what. The d hat of AB, so d twiddle of AB, is the limit of d of A and Bn as n tends to infinity. Now here I want to caution you. Why this limit exists? Both An and Bn are Cauchy sequences. Therefore, whether they are convergent or not, they are bounded. Okay. When you have both of them are bounded, this limit will exist. All right. So that is the whole idea. Okay. Otherwise, you can directly verify this. D of A and Bn minus D of Am Bm. Okay, by use triangle inequality correctly, this difference modulus is always less than or equal to D of An Am plus D of Bn Bm. Now, if n and m are very large, we know that this is less than epsilon and these are less than epsilon, or both of them are less than epsilon by 2 you can make. Okay, so here an, bn, am, bm, this will convert to 0 or some number, because you don't know what this number is. Okay, so if they are if they are Cauchy sequences and so on, you can at least whatever I want to say is this is Cauchy sequence of real number. It converges to something, both of them. This inequality is there, so this will be a convergent sequence. That's all. Now, by the very definition, if you interchange b and a, here b and a you will interchange, the number is the same, so limit will be the same. So it is symmetric. For each a, b and c, 3 sequences, distance between a and c is limit of this one, but an to cn, you can write it as an to bn plus bn to cn. So each term can be replaced by sum of 2 terms. When you take the limit, it is the limit of the sums, right? Which is sum of the limits. So therefore, what you get is Cauchy inequality. D of an cn is less than d of an bn plus d of bn cn. So when you pass to the limit, you get triangle inequality for d twiddle. Triangle inequality is true. Symmetry is true. It is a non-negative function. The only thing is, why d of AB 0 will imply A equal to B? That is not true. That is obviously not true, right? You can take just, just one of the elements you can change. Same sequence, it will have same limit. The first element you change, the limit will be the same thing. So this is not true at all, okay? However, the only thing that is not true is that the positive definiteness. Positivity is up, non-negativity is still true. The definiteness part is missing here. The D0 is missing here. Okay. D2, D3 axiom for D2 is true. Okay. So the only thing which needs to be D1, this is one of the exercises given to you earlier. If you have spent some time on it, even if you have not solved completely, these things should be easy for you to understand now. In any case, whatever is needed here in the proof of this theorem, I am going to explain it, okay? So what we are going to do, we make a relation on x hat, on x twiddle, by saying that A is related to B if and only if d hat of AB is 0. Just because d hat of AB is 0 does not imply it could be, so we are making this relation. Otherwise, there is no need. Using triangle inequality again, you can check that this is a equivalence relation. Symmetry is obvious by the definition because d hat is symmetric function. D twiddle is symmetric function. Okay. Reflexivity is obvious. D hat of AA is always 0. All right. If d hat of d twiddle of AB is 0 and d twiddle of BC is 0, then you should see that d twiddle of AC is also 0 by triangle inequality. That's all. So this relation is an equivalence relation. Let us denote this by square bracket A, the class of A, the equivalence class of A. Okay. So all Cauchy sequences represented by this A, they are all what? Equivalent to in this sense. D hat of A comma B is 0 for all B in this class. Okay, let us denote all these equivalence classes by x hat. X hat denotes the set of all equivalence classes. Now I want to modify this definition. D hat. D hat on two equivalence classes is nothing but D twiddle of AB, where A and B are representatives. Let us put this one. To say that this is well defined, what I have to do? I have to show that this right hand side is independent of what representatives I choose. So they are all same. Then this left hand side can be equal to right hand side, makes sense. Otherwise, if d hat of a comma b keeps changing as you change the representative, then this will not be well defined, right? Well definedness means that. So whenever you have choice in the definition, you have to verify that the whatever you have taken the right hand side is independent of the choice. So suppose A is equivalent to A prime, B is equivalent to B prime. We must show that d hat of AB, same thing as d hat of A prime B prime. D hat of A prime is 0. That is the meaning of A is equivalent to A prime. Similarly, d hat of D twiddle of BB prime is 0, right? Because B is equal to B prime. Again, by triangle inequality, d hat of AB is d hat of A prime B plus what? Plus d hat of A prime. So A to A prime has changed. So A prime plus this one, but A prime is 0. So this is just this one. Now I from A prime B to I go to B prime by taking d hat of A prime B plus, so A prime B prime plus d hat of BB prime. But d hat of BB prime is 0. So this is less than equal to this one. So one is less than or equal to this, but this is symmetric argument. I can start from here and less than less. Right? So they are equal. So that is what we wanted to show. So you see, all once the idea is there, all verification is very canonical, very easy. Therefore, d hat is well defined and takes only non-negative real values. Why? Because d twiddle has that property. Now, d twiddle is symmetric also. It satisfies triangle inequality also. Therefore, d hat will also satisfy triangle inequality in that one. The only thing is, why if d hat of A is also 0, that's also clear. But d hat of AB is 0. Why does it imply that d hat of A and B are equal? That is just the definition. That is just the definition. Equal means what here? They are equivalent. You see, equivalence class is the same. So this is a trick we are using to get equality. Okay. So this here equality is just equivalence classes. All right. So d hat becomes a metric on x hat. All right. So this first part is over. We have constructed this one. Now take an to be a Cauchy sequence in x hat. Each an is a Cauchy sequence, right? The equivalence class is one single element. Now you take a Cauchy sequence of that. Okay, that will be a Cauchy sequence in x hat. Let us denote the sequence an. An is a sequence now. Okay, it's ANM. So multi-index you have to use. For each fixed n, take ANM from 0 to infinity. Some people write it as a top, but I don't want to do that because that may confuse. If they are real numbers, then the power has some other meaning. Okay, so for each nn, choose a kn such that d of an kn, comma an m is less than 1 by n. So this is where I am using the fact that each an is a Cauchy sequence. Okay, so it will be less than 1 by n when for some choice of Kn large enough. For all m bigger than this one, this will be true. So this is where I have used that each n is a Cauchy sequence. Okay, this is the first step. Now look at the sequence an equal to an kn. This is one element of an of this sequence. Which one I have done? What is the kn, choice of kn? It should satisfy this one. Okay. For n1, for example, n equal to 1, a1, k1, comma, a1, m, where m is bigger than k1, will be less than 1. For 2, it will be less than 1 by 2, similar thing, like that is the meaning of this. Okay, successively, you have to make it more and more accurate. All right. Claim is this sequence. Now, this sequence is a sequence in X. Okay, capital N is a sequence in X. These points are in the X. Right? This sequence is a Cauchy in X and its equivalence classes. Okay. Sorry, this N is a sequence in here. This converges to the equivalence class of this sequence inside X hat. Okay. X hat is what? Equivalence classes of that. There's the square brackets. Okay. It started with a Cauchy sequence in X hat. I am producing a Cauchy sequence or whatever. This is an element of X hat anyway, the class of Cauchy sequence. So that will be the limit of this one. So that is the meaning of that X hat D hat is complete. Every Cauchy sequence is convergent. So this is a claim. Okay, I have to prove this one. So the most of the work goes here, that showing that it's complete here. All right. So let us carefully see that how it is coming. So here is a picture. This is your A1. I have chosen this red point here somewhere. This is A1, K1. This is A2. This is A2, K2. A3, K3, and so on. AN, KN is this sequence. Okay. So these are all sequences A1, A2, AN. What is claimed is this sequence, okay, is a cluster point of all this. Namely, all these things after a certain stage is shown here. Some epsilon ball here. Actually, this is of epsilon by 2 ball. So this radius is epsilon. All of them are within this. The tail end of this one. These points may be somewhere. The tail end for all of them will be here. So something may be here omitted. Many things are here or omitted, but the tail ends of the tail ends are here. That is the meaning of this one. Given any epsilon ball. So this is what we have to prove. This is the picture, you can keep it in mind, that's all. All right. So given epsilon, this is the ball. Given epsilon, tail end I have to find such that this fits all the sequences after a certain stage in both ways. That's what I have to choose. The first choice is, given epsilon, choose the n1 itself. N1 is the 1 by n1 less than epsilon by 3. You can choose epsilon by 4 also if you want to be careful. Okay. So here there is nothing, this is just real numbers property. Since an, okay, is Cauchy in X hat, okay, there exists an n2 such that d twiddle of AR AS is less than epsilon by 3 for every AR S less than n2. Remember, this d hat was nothing but d twiddle of the representatives. Okay, these are classes. AR, if you put a bracket here, d hat of AR, d hat of AR, and AS here brackets. That is less than epsilon by 3 is the statement for R and S bigger than or equal to N2. But I don't have to put hat here. I can directly put d twiddle of AR and AS. Remember, AR and AS are themselves Cauchy sequences. And what is the definition of d twiddle? D twiddle was the limit of as n tends to c ARN ASN of the original distance between ARS and ASN. Okay. So finally, everything is happening in the metric space X. Now you take the maximum of this N1 and N2. Okay. That is N3. I want to show that AR AS is a Cauchy sequence, first of all. I haven't yet shown that. Without that, it will not be it will not be in X-twiddle, so it will not be inside X hat. The first thing is to show that A itself is a Cauchy sequence. That means what? For any epsilon, I must find a R and S such that the distance between AR and AS is less than epsilon, right? Or epsilon by 3, whatever you want to say. So that's what I have shown. So fix R and S were bigger than N3. For all of them, I must show that DARAS, this is ordinary distance between the metric, this is the points of X now, right? This is less than epsilon, I want to show. Okay. So how do I show that? So starting with these choices, you see, R and S are bigger than N3, so they will be bigger than N1 and N2. So both these hypotheses will be applicable to. D twiddle of ARAS is already less than epsilon by 3 because of N, they are bigger than N2. Okay. So this implies that there exists in N4. Now I am using the definition of D twiddle because it was taking limits, right? The limit is less than epsilon by 3. That's what I have to show. That is what it is. So D of ARM ASM for large enough M is less than epsilon by 3. R and S are fixed here. It is the variable here is the index is M. Okay. For M sufficiently large, namely N4. There is some N4. Okay. So this is one equation. Okay. Now you choose M to be bigger than. M is bigger than all the time. If it has to be bigger than something, I can choose it even bigger than that one. M to be bigger than KR, KS, and N4. Okay. Then you can apply both this what is this 18 here? See, for this one, M should be bigger than KR, KN, right? So I am applying it for N equal to R, so it must be bigger than KR. Applying it for N equal to S should be bigger than KS. So I am taking it bigger than KR, KS, as well as to satisfy this bigger than N4 also. Okay, so both 18 and 19 are available to me. So I just use triangle inequality now. D of ARAS, what are ARAS? By definition, AR, KR, AS, KS. So this is the ordinary distance of the metric space X, right? So triangle inequality, right? It is three different sums, namely AR, KR to ARM. Okay? Where M is chosen to be larger than all these. Plus ARM to ASM, jump to SM. From ASM, come back to ASKS. So this is triangle inequality. Okay, this is less than equal to this one. From 18, these two things will be less than epsilon by 3. From 19, this will be less than epsilon by 3. So totally less than epsilon. So this is a Cauchy sequence is what we have seen. The next task is that the original sequence of classes AN converges to the class A. That's what I have to show. This is what I have to show. Okay. Look at D of ANM and AM. What is AM? Remember this one? It is little a m k m. Right? So that is whatever it is. This is a number. This is just an element of x. They are all elements of x. So d of a n m makes sense. Which is less than equal to d of a n m to a n, and then a n to a m. So this is just triangle inequality. Okay. Now the first term on the right hand side, this one, is less than 1 by n for m bigger than kn. Right? This kn was chosen such that, look at this very first choice, an, kn, anm is less than 1 by n. So that I am applying it here. Okay. So this term is less, as soon as m is bigger than kn, this term is less than 1 by n. All right. This distance, the second term, can be made any smaller than anything once you choose n and m large enough. That's right. For large enough, this can be made less than m and n, because just now we have shown that this is a Cauchy sequence. Therefore, d hat of an, a capital A here, the class A, which is by definition d twiddle of an and a, which is again by definition limit as m tends to infinity of d of this sequence a and m and the other sequence a m. Now here m tends to infinity. Okay. Each term is less than epsilon, the limit will be less than epsilon. After a certain stage, sorry. So limit will be also less than epsilon. Okay. So for this will apply when n is large enough, because I have an n here. Okay, so this is epsilon by 2. I have to make this n less than epsilon by 2 to make it epsilon. So n must be large enough. How large? 1 by n should be less than epsilon by 2. That's all. Therefore, if this is true for every epsilon, look at here. This is one single number here. This less than epsilon for every epsilon. Therefore, the limit as n tends to infinity, which is part d hat of a and m, okay, is 0. For large n, this is less than epsilon. So if you take the limit of this one, this will be 0. That is precisely the statement that this sequence converges to this one. Okay. When does a sequence xn converge to x in a metric space? Distance between xn and x limit is 0. Okay. So what we have done, we have just completed the construction and property 0, that x hat is a complete metric space. Now we have to verify 1, 2, 3, 4. They are all easy. All right, hard work is already done. So it remains to prove that 4 properties, 1, 2, 3, 4. Okay. The first thing is I have defined eta. Eta of x to x hat, that's what I have to define. Given any x belonging to x, consider the constant sequence x, 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 x. The nth term is x. Look at that sequence. That is obviously a Cauchy sequence. Take its class. That's an element of x hat. Okay? So this way I get the function eta x is the class of Cx. Obviously, eta is injective. Okay? Why? Suppose eta x is equal to eta y. Cx is in the same class of Cy. What is the meaning of that? That distance, the limit of that, you see, you have to take the limit is equal to 0. But limit is here xy, 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 d of xy, xy, xy. So limit itself is dxy. So that is 0 means x equal to y. X is a metric space. Okay. So this is clearly a injective mapping. Okay. Actually, we shall prove that, we can check that it's distance preserving. What is the meaning of this? Take 2 points x and y. Cx and Cy distance is also dxy. So that is the meaning of this distance preserving. d hat of cx, cy is equal to d of xy, because it is both of them are constant sequences. Okay, so it is automatically distance preserving and hence injective mapping. What is the second thing here? I forgot. What is it? Eta is dense inside X hat. The image is dense in X hat. Take any open ball in X hat, you must find a point eta x inside that, which must intersect eta capital X. So that is the meaning of that, right? Density of eta x. Okay, so here it is. We shall prove that every open ball in X hat intersects eta x. Okay, given xn, a sequence, Cauchy sequence, and its class. Okay, take a r positive and take an open ball around that of radius r. Okay, I want to get an element of the metric space so that the constant function, constant sequence, the equivalent class of the constant sequence is in that ball. That means its distance from xn to that must be what? Less than r. So for that, choose a k belonging to n such that this is a Cauchy sequence. dxk, xk plus m is less than r for all m. Okay, once you have chosen k, for all numbers bigger than k also this will be true. So this is definitely true for k and xk plus m less than r for all m. Now it follows that once you have chosen this one, look at the constant sequence xk. That sequence, okay, has distance less than r from d hat of xn. Okay, so that is why this eta of xk now, it belongs to this open ball. Okay. Finally, take any two metric spaces and an isometry F. That isometry itself extends to the whole of x hat to x1 hat to x2 hat. So this is stronger than saying that no, x1 hat is unique up to isometry. That is the meaning of this. That's what we want to prove, but we are proving it's strong. The actual isometry, each isometry extends. Okay. So how do we prove that? Isometry means distance preserving. Look at the construction of x1 hat and x2 hat. It just depends upon the metric there. That's all. So in isometry, it is metric equivalence, right? For everything it will be Cauchy sequence preserved, everything will be preserved. Equivalence will be preserved, that's why. So that's what you have. Take a sequence, Cauchy sequence in x1. F hat of A, which is f of ANs, that sequence, that will be Cauchy inside x2. Even just similarity would have given you this one, right? Here we have an isometry. Okay. Since isometries preserve Cauchy sequences, first of all, F hat is well defined from x1 twiddle to x2 twiddle. Okay. Here take a Cauchy sequence. F of that will be a Cauchy sequence here. Okay. Now you see that this F hat is an isometry of the corresponding D1 twiddle, D2 twiddle, the pseudo-metric spaces. The D2 twiddle distance is preserved by this F hat, F twiddle. D2 twiddle of F of An, F of Bn, by definition, is the limit as n tends to infinity, D2 of F of An, F of Bn. Each F of An, F of Bn is the same thing as D1, distance between these D1 of A and Bn. right? Because F itself is isometry. If this limit is d total of AB, the given sequence A and Bn. So that is the meaning of that. F is, distance preserving from D1 to D2, D1 twiddle to D2 twiddle. Okay. Clearly, F hat also preserves equivalence relations and hence defines an isometry F hat from X1 to X2. Why this preserves equivalence? What is equivalence? An is equivalent to Bn if the limit of distance between A and Bn is 0, right? Distance between f of A and will be also 0 limit. So everything is preserved. That's what you have to verify. So you get a map from F twiddle to F hat here, from X1 hat to X2 hat. The class here goes to the class there. Okay. And the distances in D hat is same thing as distance we have defined for representative. So they are preserved. So it is preserved. So it is an isometry all about. So the net conclusion here is the construction depends only on the isometric class of X1, X whatever, starting with. If X1 and X2 are isometric, X1 hat and X2 hat are isometric. Okay. The last one is, suppose X itself was complete. Then I have to prove that, this eta is surjective. Then eta itself is an isometry. Okay. So why it is surjective? Take any xn in X hat. Okay. The class represented by a Cauchy sequence xn in X. That is the meaning of this X hat, right? Since X is complete, it has a limit. This xn has a limit. This limit is independent of the Cauchy of the equivalence class. All the sequences, whatever sequence you take here, okay, representing this one, they will all be convergent. They will be convergent to the same X, because the limit of distance between xn and yn, that itself will be 0. So if this is x and that is y, x will be equal to y. So there is a unique limit here inside X. Okay. Now, very easy to verify that the constant sequence Cx itself, the equivalence class, itself will be in the class of Xn. So you have to show that these two are equivalent. What is the meaning of that? Distance between Xn and this Cx, that is tends to 0. But that is the definition of that Xn converges to X. Okay. So that is the meaning of this one. So this just shows that eta X is equal to the class Xn. So eta is surjective. Okay. So that is more or less completes several things that we have in mind about metric spaces. That doesn't mean that the study of metric space is completed. There are many things. But now onwards, we will concentrate more and more on general topological spaces, bringing in metric spaces only to strengthen the results that the topological results will give you about metric spaces. Okay. Any questions? Here are some exercises. All straightforward exercises. Nothing to do with completion, of course. Okay. Just ordinary exercises. This is about the product, finite product of metric spaces. All right. This is about, again, finite many things. Then you want to take it as the maximum metric. Just like L infinity norm, you can do L infinity, the D infinity metric here. The D infinity corresponding to maximum, that infinity symbol. Okay. So that is the next chapter now. So if there are no questions, we will stop here. Thank you.